I'm very happy to introduce group one, who's going to tell us about initial graphs of closed graphs, vertex-decomposable complexes, and cat graphs.
Hello, everyone. Thank you very much for coming. This is Armando, and I'm Josiah, and today we'll be talking about initial graphs of closed graphs, vertex-decomposable complexes, and the cat graph.
Yeah, so let's start. We have our graph and we have our binomial H ideal, but this is a binomial ideal, and it would be nicer to work with monomial ideals, so we're going to define two monomial ideals. The initial ideal, which is just generated by deleting monomials of all the monomials in the ideal, and the generic multi-graded initial ideal that, thanks to Conahcyt, Denigri, and Gorlin, we can describe in terms of the paths in G. And turns out that when G is a closed graph, we have a very nice description of the initial ideal because it is generated by deleting monomials of the generators of the binomial H ideal. And well, turns out that algebra is still too hard. So algebra turned to combinatorics once again and made simplicial complexes out of ideals. So a simplicial complex is just a subset of the power set of n, such that if we have any set in delta, then any subset of f will also be in delta. And the elements in delta are called faces, and the maximal faces with respect to inclusion are called the facets and are denoted like this. And we can describe a simplicial complex only using its facets, like here. These are the facets, like you can see here we have like a filling in 1, 2, 3, but not in 4, 5, 6, because this is not a facet, the simplicial complex. And even though I'm talking about n natural numbers, we can use any symbols we want. And how do we obtain a simplicial complex from an ideal? We take the Stanley-Reisner complex. All the monomials that are not in the ideal, this needs to be a square-free monomial ideal. Like here, for example, x1, x2 is not in that ideal, and neither is x2, x3, x4. So we obtain this simplicial complex. Okay, so now we can create two different simplicial complexes out of these two ideals. And we have these nice properties, but why do we care about them? Also has a really nice algebraic interpretation in terms of the minimal primes being disjoint. And we also know that vertex-decomposable implies shellable. So we're not really going to get into what shellable means, but just keep in mind that it's implied by vertex-decomposable. So being pure just means that all the facets have the same cardinality in a simplicial complex. Like here, it's pure, but the other one is not pure. And being vertex-decomposable is a recursive definition. Either delta is an empty simplicial complex, delta is a simplex, which means that it only has a facet. Or either we take a vertex V from delta and take its deletion, the faces that do not contain V, and the link, the faces that do not contain V, but if you add V, then you get a face. And if those are vertex-decomposable, then the whole thing is vertex-decomposable. Like here, for example, in this simplicial complex, the deletion of x1 would be that, and the link would be that. Both of they are simplices, so it's vertex-decomposable. So what is the problem? We're trying to see for which graphs G, when G is closed and connected, and we take the delta G and the delta in, when is that pure, shellable, and or vertex-decomposable? And yeah, what do we find about G? Can we tell something just by looking at the graph? Actually, it turns out we can. That's why we define the cat graph. There you go. This looks more like a cat, but it's not a cat graph. Here is a graph like with an induced cat, and here's a graph that has no induced cat. So here we say this is cat-free. And from now on, we're going to focus on cat-free graphs. Oh. And we have this beautiful theorem by Herzog, Hibi, and Ostrowski. And this tells us that JG being omega is equivalent to JG being Macaulay. G is cat-free as well. And very important thing, if G is cat-free, the intersection of two maximal cliques of G happens at most one vertex. And also delta in of the delta G will be pure. This was also shown by Polony, Macchia, Rinaldo, and Strasanti. And we have this theorem from Van Tuyl, which is not exactly what we were looking for, but it's equivalent to the delta in that we're interested in. So the work was pretty much done there. So far we have these implications. We really know what happens in this branch of the tree, but we don't really know a lot about this branch of the tree, about the delta gene. And that's what we'll try to do for the rest of the talk. Oh, no.
Well, what about delta gene? As like Armando says, when we have a cat-free graph, we can see the maximal clicks, like intervals, and they all intersect in one vertex. That vertices, we name it the pivots, but we can extend this definition for graphs with a cat, like the intersection between two maximal clicks. So this is a very important definition because with this, we can prove this proposition. The proposition right here says that if we have a cat-free graph, closer and connected, and the delta gene is pure vertex decomposable. The proof for this is by strong induction. We suppose that, well, we want to know that this is vertex decomposable. So we suppose that, we are doing the strong induction in the number of pivots. So we suppose specifically that this graph, the delta gene from those, is vertex decomposable. So this is like a sketch of the proof. We have the original simple shell complex, and like Armando says, it's like a recursive definition. So in this part, if we do the relation of a lot of x's, we obtain one of the induction hypotheses. Right here, all the links are equal to this link. So we only have to prove that this link is vertex decomposable. Here we delete another vertex, we obtain another induction hypothesis, and here it's not equivalent to the induction hypothesis, but we know that this is vertex decomposable by a lemma proved by proven Villera. And since this is vertex decomposable, we obtain that all the last part of the tree are vertex decomposable, and we can conclude that this is vertex decomposable. So this is like a corollary of this proposition, and it's like a merge of everything that we know. Here we have the theorem, Van Tuyl, the Bolognini, Macchia, Rinaldo, Strasanti. Here the Heston, Hibi, Osugi, and the union is with the cat-free graph and the delta gene, the properties for delta gene. But maybe the cats are not that bad. Well, we worked with only cat-free graphs, but maybe the cats deserve another opportunity, right? So we copied a lot of examples in Macaulay too, and we have this conjecture for future research that for every closer and connected graph, the delta gene is vertex decomposable, even if G has a cat. The problem here is that the delta gene when G has a cat, this is not pure. So we have to use the general definition for vertex decomposable, and the pivots are not just one vertex. So maybe we can extend the proof, but for now it's only a conjecture.
So far, we've been talking a lot about delta gin, and we've been trying to keep cats away from the gin, which is good because no one wants drunk cats. But now we should talk about the delta in, right? And as we saw before, we can take a graph, we can turn it into some algebra by taking the binomial edge ideal, and then we can look at the initial ideal, and to make our life simpler, we can look at the initial complex delta in of G. Although you guys just saw that complexes are not that easy, as the name complex suggests. But in the case of an initial graph, when we're looking at a closed graph G, we can actually reduce the initial complex into something called the initial graph. And graphs, it turns out, are a lot easier to study.
So it's quite miraculous, actually. When G has a closed labeling, the initial ideal is actually just the leading monomials. Just looks like an edge ideal. So it's a very natural question. What happens when we make it an edge ideal? What happens with the graph? Well, it's so natural. The vertices for every vertex in the original graph, we have we double them. We have X vertex and we have Y vertex. And every time there's an edge in the original graph between like I and J, we put an edge between Xi and Yj, and it looks really nice. It's like we force the graph to be bipartite. Every time 0 connects to 1, we have x0 connects to y1, 0 connects to 3, it's 0 connects to y3. And in particular, all the edges slope down like this, because every time we have I connected to j, I less than j, we have I on the x side, j on the y side. So question, we'd like to recognize when any one of these graphs actually has like a secret deep algebraic interpretation, and we want to figure out when it actually is isomorphic to an initial graph for a closed and connected graph. And we have an algorithm that does exactly this. It's 2 parts. It returns true if and only if it's isomorphic to the initial graph of a closed graph. And if it is isomorphic to an initial graph, not only does it return true, it also such that it looks like an initial graph, as in everything slopes down like this.
So our goal is yes, okay. Our goal is to take a bipartite graph H and look at it and determine whether or not it can be labeled to look like an initial graph. Because we're looking at an unlabeled graph H, in order to determine this, we need to look at the combinatorial properties of H as opposed to of an initial graph. So we're going to study the combinatorial properties of an initial graph G, where G is connected and has a closed labeling. One of the most immediate properties that jumps out to us is that in any initial graph, there are exactly 2 vertices of degree 0. And if our graph G has vertices labeled 0 through n-1, we actually know the labeling of these vertices. We know that the vertex xn-1 in the initial graph must have degree 0. We also know that the vertex y0 in the initial graph must have degree 0. This means that if we're presented a random bipartite graph H, we can look at vertices of degree 0 and immediately know what their labeling must be. This is a really nice property. And now we have another combinatorial property of initial graphs that actually comes from a combinatorial property of closed and connected graphs. If we have a closed and connected graph, it turns out that we can view the graph G as a stack of complete graphs. So over here, we have a graph G, which is closed and connected on vertices 0 through 5. And if we look at the first 4 vertices of these, we can see that they form a maximal clique. They have a K4 structure. This means that in the initial graph, we must be looking at the initial graph of a K4 when we look at the vertices x0 through x3 and y0 through y3. Continuing this process, we can see in G, the vertices 1 through 4 also form a complete graph K4. This means there's another initial graph of K4 in the initial graph. Finally, the last 3 vertices form a K3, and so there's an initial graph of a K3. This motivates us to look at the initial graphs of complete graphs so that we can determine what initial graphs look like. Besides having 2 vertices of degree 0, initial graphs of complete graphs have exactly 2 vertices of degree 1. And if we're looking at a Kn, we also know what labeling these vertices of degree 1 have. Importantly, xn-2 will be a vertex of degree 1, and y1 will be a vertex of degree 1. Now, complete graphs have a recursive structure. If you take a Kn and remove 1 vertex from Kn, what is left is a Kn-1. This translates to a recursive property about initial graphs, meaning if you find a vertex of degree 1, for example, x2 in this picture, and you look at its unique neighbor, and you remove both of these vertices, what is left is a k2. An initial graph of a k3. We started with an initial graph of a k4, we removed 2 vertices, and recursively we have the initial graph of a k3. This leads us to the properties that allow us to construct an algorithm. Oh, so here is a bipartite graph H. We know that it's an initial graph, but it's been scrambled, and we'd like to reconstruct the ordering on it. So first, we look for the vertices of degree 0. We give them the labeling that they must have. Now, we find x4, which is a vertex of degree 1. We find its unique neighbor, y5. We know what they must be labeled, and so we remove them. And because of the recursive structure of complete graphs, we know that after removing these 2 vertices, we can recursively search for vertices of degree 1 and construct a complete labeling on this graph that makes it look like an initial graph.
So we can see how with that structure that Josiah just described, we would get a good ordering of an initial graph if it were like possible to make it into an initial graph in the first place. But what are we actually doing here? We're just finding degree 1 vertices and we're chasing them down one after another. We're putting them in a chain and we get this zigzag property. We get this zigzag subgraph structure underneath, and it's not enough. It is good because if we have the zigzag structure, then we proved there's only 2 ways to order a bipartite graph with the zigzag structure, such that all the vertices are down right as before, they all slope downwards. But we can possibly cheat this algorithm by pretending we have a zigzag, oh, we have some edges on top, it's not good enough. We can possibly make something that fools the algorithm by having a zigzag, but it shouldn't really pass. We can check, since it only has 2 orderings, that there is no possible way that it could look like an initial graph. So we have to add another condition. But it's okay, because the whole reason we came up with this algorithm in the first place was to find initial graphs of complete graphs. So all we have to do is check if the algorithm says that there should be an initial graph here, then we have to check that there is actually one there. In particular, what we do, we say, hey, this one has degree 3. That means there should be a K4. There actually is. That's good. In this example, it's the initial graph of a complete graph, of a closed graph. So our theorem shows that with the 2 algorithms, it's isomorphic to an initial graph if and only if it passes the first step of the algorithm and satisfies the second condition in the algorithm. And every initial graph will complete the algorithm. And if it does complete the algorithm, then the algorithm given by the first part described by Josiah will give an initial ordering such that it's like congruent to the initial graph.
Great, questions and speakers. Anybody else ask a question?
Can you what was the last thing in the thank you slide?
Shut up.
Just a thank you for your attention. But I was expecting something a little more spicy.
I was too.
I mean, I do have I do have a real math question. How optimistic are you that you can prove this for graphs that also have, like this vertex decomposability for graphs that also have a cat? I know your current method fails. Is there a way to, is there a way to somehow modify it and get the result, or you need a totally new approach?
No, I think that we can just modify the proof because I think that we can define the delta G with the definition. Let me put the motivation for the pivots is for describe the delta G. So if we can describe the delta G with the definition of pivots, maybe we can do the same right here, but I don't know if we can use exactly the same decomposition. Maybe we can do it by induction, but I don't know if the same decomposition works.
More questions? Okay, if not, let's thank the speakers again.